Good evening. Thank you for a very kind introduction and very interesting introductory notes on causality. My name is Karina Shyrokykh. I work as research statistician at Ericsson Consumer Lab, and what we do, we study consumers. And today I would like to talk about causal inferences using observational data, and the guys nicely highlighted different scenarios under which you might be interested, in fact, to have these insights. In this particular case, I'll be talking about time series cross-section, and in this format or in this context, I'll be using interchangeably time series cross-section and parallel data. So in some disciplines, I know that these two terms might mean slightly different setups, but in my talk, I would imply basically the same data structure using these two terms. So, as guys also very nicely presented in the beginning, when we talk about analysis in data science settings, right, when we talk about machine learning problems, we usually want to predict a particular event happening. We want to predict, for instance, whether this transaction is fraudulent or it is a normal transaction. Sometimes we want to use some tools to facilitate decision whether we have to approve this application for loan or to disregard this application. Or we want also to predict customer churn behavior. So these are more or less typical tasks for data science in most of the cases. But sometimes we might be also interested in knowing not only of when a customer is more likely to leave our company or our product. We also want to know why the customer wants to leave, or how can we actually avoid such situations, what can we do to make our customers stay with us. And this is a basic task, let's say, in different disciplines, in most of the social science research, but also life science research. That is one of the topics or one of the questions that you would want to answer. For instance, what is the effect of smoking on a person, right? Chances of obtaining cancer. That is one of the questions that we would want to answer using causal inferences. Another question would be, okay, we have, for instance, a very bad gun situation or crime rate in our area. So whether imposing or introducing gun policies would actually help us fight back crime rate in our districts. So topics like that could be studied using these setups. These are the questions that we want eventually to answer. But when we talk about causality or causal effects, what we are talking about, it is about two alternative universes. We know what things are looking like in our universe, right? Because we have treated, we have applied a particular variable, and we can see the outcome. But we want eventually to know what reality would have been had we not applied this treatment. So again, this is something that would be possible only if we had an opportunity to observe two parallel universes. Unfortunately, we don't always have this opportunity, too bad for us, so we cannot think or we cannot say how things would have been had we not applied treatment. For instance, if I want to see what is an effect of smoking, I could run an experiment. I can split you into equal groups, I can assign you to one or the other group randomly, and I can assign you smoking, well, one part of the group, right? And the second group won't be smoking. And then I would measure different health behavior, right, or health variables before you were introduced to smoking and after you started smoking. And by that, I would try to understand actually what is the effect of smoking. And this is the closest we can get in our real settings, right? Because I cannot impose smoking on you and not impose smoking on you, on the same group of people. You can be either imposed or not impose smoking on. So, this is what causality is about. It is trying to study counterfactuals. We have facts and we want to study what could have happened had we not applied the treatment. Yes, it is impossible. But the closest we can get to understanding causal effects, it is actually running experiments. So, and as I gave you an example of smoking and the effects of smoking on your health, that's how we would usually do that, right? So that's how you would run an experiment, which implies that, first of all, we have random assignment of treatment. I randomly assign you to the control group, non-smoking group, or to the smoking group. And also I can manipulate the treatment. And by treatment here I mean the variable that we can manipulate, right? So I either apply treatment or some event to you, or I do not apply it. When I say treatment today, I will not mean any medical implications. It is just, and does not need to be actually a binary variable, yes or no. It can be continuous variable as well. It's just to make kind of terminology clear. But again, when we talk about smoking and effects of smoking, we all know that it is bad for our health probably. So it won't be ethical for me to impose on you some behavior that I assume will lead to some negative results. So in most of the cases, well, in this case at least, it is unethical. There are also other cases when it is unethical to apply this random assignment to a treatment. And then what else do we do? Can we use any other sort of data, or can we do anything to try to have causal inferences at the end? And the answer is yes. So we can use observational data to draw causal inferences. And in these settings, we use observational data, and we heard about observational data and causal inferences a little bit just a few minutes ago. So in these settings, the treatment cannot be manipulated, and it is not randomly assigned. But still, what we want to do, because our golden rule is to study counterfactuals, or intent is to study counterfactuals, so when we have observational data, our intent is to get as close as possible to the study of counterfactuals, to understanding whether what would have been an effect had we not applied the treatment. And basically, causal effect in these premises would mean a difference between what has happened and what could have happened had we not applied the treatment. So this will be the size of the effect, right? This difference. So, and today I will be talking about observational data and causal inferences on observational data. And most of my talk will be about importance of assumptions, underlining assumptions that you have to respect, you have to check for in your data to be able to get as closest as possible to the counterfactuals, right? To get as closest as possible to study what the behavior of your treated units would have been had we not applied the treatment. So, these settings, given that we are trying to get closer to experiments, the best we can get in absence of the second parallel universe that we can observe, since we're trying to get closer to the experiments, these methods would be called quasi-experimental. In literature, they often called quasi-experimental methods. These are broad classes of methods, and of course, this is not extensive list of all the methods, them anymore. But for instance, the panel methods, the one that I'll be talking today, again, this I'll be using, the term I'll be using interchangeably with time series cross-section. There are also matching techniques, instrumental variable techniques, of which we have heard a little bit today, and also the regression continuity, as just to mention a few techniques or models that you could use in order to draw some causal inferences. So panel data is a case of longitudinal data when you have a fixed number of units of your analysis that you observe over a fixed period of time. Let's say we have, 30 people observed over 10 years, right? So it is the same people observed over the same time periods. And a powerful opportunity that we have with panel data analysis, it is that we can actually control for those unobservable variables, right? We had these personal features that the guys showed during the first part, right? So these unobservable features, which are time invariant for every individual, if we talk about individuals as units of analysis. But this could be companies or countries, for instance, right? So we can account for these unobserved characteristics, so to say. Panel data also is a powerful tool because it allows you to include into your model different levels, variables at different levels. For instance, students that are in the same or kind of placed in a school, and schools are in districts, and districts are in states. We talk about the US, for instance, right? So by doing that, you can avoid complicated hierarchical models with panel data. And again, so having these two dimensions, time series and cross-section combined together, we can actually avoid two big issues in trying to do causal inferences. It is, again, confounding variables and reverse causation. So this is an example of panel data, time series cross-section. So we have in this part, I don't know whether you can see it, but well, this is a cross-section example. One, you have, for instance, units, let's say individuals. Information about these individuals is collected in one variable, and then you have other kind of types of information collected, other variables. So, and that will be data collected in one particular period of time, right? In time series, you will have information about, let's say, one individual or one firm or whatever state. The data will be collected across a few time periods. When we talk about time series cross-section, we combine these two elements. So we have, let's say, a number of individuals observed over a few time periods. So by that, you obtain more degrees of freedom, obviously, and you have opportunities to draw causal inferences, but also deal with reverse causation. And examples, of course, of this data structure could be numerous, uncountable, probably, and you can think of those yourselves. But for instance, it can be social or economic changes over time in a few countries, for instance, or regions. It can be individuals' growth or development in different contexts, not only physical, but also mental, etc. Or, for instance, it could be an economic growth in EU member states, right, over, let's say, 20 years, and then it would give you quite many observations in comparison to cross-section or time series dimensions of the data. So, and how do you usually calculate them? You multiply the number of fixed units by the number of time periods, and that's what you get. And then your unit of observation would become trivial. This will be a unit of analysis, right? So, and just to give you an example, to compare different setups in a more formal way. So here we have an example of cross-sectional data estimated with OLS, least squares, right? So, and here we have, and again, on the terminology, this is the outcome variable. Sometimes we'll call it dependent variable because, again, these are synonyms in different disciplines. An intercept, a slope for this particular variable, and the error term. So, and here the difference is that here we have subscripts for individuals, so these are units of analysis and these are time periods. And this is the only difference between cross-section and time series data. And when we talk about panel data, we'll basically have a combination of two. As you can see, it is just simple combination of two. Yes, so, and then when we talk about panel data, there are of course many models to model relationship in that data. The simplest probably model, it is a pooled model. And pooled least square model is a model where you assume, you impose this assumption that effects will be the same across all of the units of analysis. So you think that whatever, when I give you treatment, for instance, smoking, and I ask you to smoke and you kindly agree, risking your life, I would assume that I will observe more or less the same effects of smoking on everybody. Right? This is unlikely to happen in physical world, we know that, because there are many characteristics of our lifestyle that might define the outcome of your smoking. And therefore, assumptions and testing for the statistical assumptions is very important in these settings. But when we have pooled model, what we assume that effects of smoking will be the same on everybody. So this model is a good case for trying to understand average effect of a treatment variable. So, and that's, again, how it looks like. And when we talk about hypothetical examples, for instance, of a model that would try to analyze effects of a treatment variable on the outcome variable, so this is just a few examples. So again, for instance, we can here study how democracy can affect GDP in the country. This we can see that it is a time period T here and there. So it's a static model, so to say. Then we could also decide to study effects of democracy on GDP, taking into consideration past realizations of GDP. And that, in this particular sense, it is needed because here we have violation of a statistical assumption. Basically, we have autoregression, and that's how we correctly, and I'll talk more about that, so just don't be afraid. We can assume that for the treatment to be kind of seen in the outcome variable will take some time, right? We introduce a lag of the treatment, right? So it is t minus 1. We assume that after I apply smoking to you, it will take some time before I can see whether you have developed cancer, right? That's what you can do with that. And again, here we have lag-dependent variable to fix for autocorrelation. Just an example. So, and again, these all models assume that the variable democracy will have impact on GDP, and the effects will be all the same across all units I, across all of the units, right? And in this case, it is states. This can be states, regions, whatever is interest for you. So, because you assume that the effects are the same, it's basically called pooled model. And the statistical assumptions are basically related to 3 big kind of chunks, so to say. I will talk more about this just to very quickly kind of name you. So, so first we have a strong assumption that covariates are exogenous. We also assume that errors across units of analysis or individuals, let's say, or states, that they are uncorrelated. Or here we also assume that error terms across time periods are uncorrelated, so that is very important. And another assumption that we have that we have homoscedastic errors. So basically variance is the same for every unit. You have the same variance, and it is equivalent to variance of the whole set of your individuals, so whatever is a unit of analysis. So I'm now talking about the assumptions. So this is the autocorrelation picture that I have there. So basically, when we have autocorrelation in our data, it basically violates the assumption that we have independent errors in our data. So basically, there is dependency between, let's say, your current observation and observation at some other period of time. It can be previous, or it can be two observations back, 2 time observations back. Like here, for instance, we can see that observations here kind of very much dependent on the previous observation. So knowing this point, you know what the next point would be, more or less, right? It cannot jump all the way up, or it cannot go all the way down. So this is the case of autocorrelation and this violation of one of the assumptions. You can actually detect whether you have this issue in the data by using, for instance, Woolrich test, and you can also detect the order of your autocorrelation by using Ariana-Bond test. And that's where you introduce lag-dependent variable. For instance, so you introduce observation for a variable at t minus 1, for instance, if it is first order autocorrelation. And I'll show you how this look like lag-dependent variables, for instance. Yes, then you also can have the issue of non-stationarity, and we have heard a little bit today about spurious correlation. So that is where it's all coming from. So when you have both the outcome variable and the treatment variable having some trend in the data by itself, it can lead to the problem of spurious correlation. And then we can get these very fine results, like, you know, money invested into science and cases of homicide, or whatever the example was. So these essentially have nothing to do with each other. What they have in common, these variables, is that they have a trend, right? They are just trending. And most of the data, when it comes to socioeconomic data, they are all trending. There are some trends, like GDP, right? It's not random realization. It usually has, if we don't have any economic problems, like economic crisis, it usually goes slightly up. Well, depending on the country, of course, but still, there is a trend. So it is one of the things that has to be checked among the first things, and otherwise you can run into big troubles, like saying that money invested into economy or money invested into science leads to homicide, which obviously has nothing to do with each other. And to detect this particular issue in your data, you can by using different tests, of course, and different tests depend a lot on what sort of data you have, what is the size of your n, units of observation, or not, sorry, how many units of observation, the ones I denote I in this case, and how many time periods you have as well. So depending on the structure, how you have it, whether it is a short time series or it is a long time series, you'll have different tests for that. Just one has to take that into consideration because this test also has some assumptions. So, and let's say you found that you have this particular issue and you are afraid that you could, by mistake, attribute you can attribute this trends, and you can mistake it for correlation or, God forbid, causal relationship. Then you should differentiate your model, and instead of taking a level model, you can take a difference between your level model at this time period, for instance, and the previous time period. That's how you solve it. And I've been shown that I have now 5 minutes, so I will try to talk very fast. So another issue that you can have in your data, and in fact we do have that quite often, it is heteroscedasticity. It is the instance where variance for different units is different, right? And of course you need to account for that because it violates those settings that we would want to have in a research design similar to experiments. So basically you can test for this particular issue using modified wall test, and you can fix it introducing, for instance, final corrected standard errors. Another issue that you can have in your data, and in fact we often see this data when we analyze regional data, is that you could have regional clustering. And then you violate the assumption that basically individual units of analysis that are independent of each other. So they might be dependent sometimes. And in this case, it is a poverty map, and you can see that there is some regional dependency. So you need to fix for that. So again, there are some tests for that, and you can use, for instance, spatial models to do that. You don't need necessarily to apply panel data models, but you also can fix for that using Driscoll-Craig standard errors, for instance. And that is the very last, and probably the most important thing, the most important assumption and violation thereof. It is when you see that your units are not homogeneous, when you see that the intercepts are actually different, and that can lead to very big issues, very, very big troubles, going all the way up to drawing contradictory or opposite conclusions from what they should have been. And I'll show you an example of that. So you can detect whether you have a common intercept or different intercepts for different units by simply plotting and seeing what are the intercepts. You can also run an F-test on dummy variables for each of the units. Basically, introduce dummies for units. And you can fix for this problem by treating these different intercepts as being due to random or as being due to a systematic component, unobserved variable that you cannot capture. That is where it's coming from. It is fixed effects model. So you think that it is unit characteristic that you cannot disregard. It is something that drives its behavior. So, and that's how the problem looks like. When you have heterogeneity, that's what pooled regression model gives you. It gives you one. So you have 2 units of analysis observed over time. So these are 2 units, let's say, and they have individual slopes, right? So they have these are basically betas. Anyhow, you have this pooled model or pooled line, and in this particular case, it correctly estimates the effects. Here, it overestimates because you can see the individual effects, right? And this is just kind of overestimates, so to say, the effects. Here, it underestimates the effects, and here, it gives you a completely different picture from what you actually have in your data. Therefore, you need to fix for, or you need to actually understand whether you have this issue in your data, whether it is very heterogeneous or homogeneous data. In fact, and in this particular paper, the authors, what they do, they go through A-level journals, they collect data, what people were using panel data settings, and they actually show that, actually quite a lot of research is about that. That's fascinating. I advise you to read this paper, that's really interesting. So let's not be among those whom will be analyzed in some 20 years for making mistakes. Yes, so basically, again, you can use random effects to fix for unit heterogeneity, and then you assume that there is no systematic component and that the different intercepts are only due to random. Yeah, whatever. Random processes. And fixed effects would assume that, well, it is a non-stochastic process. There is a systematic difference between the units of analysis. And if we talk, let's say, about countries or companies, that's what we assume, that they have intrinsic characteristics, let's say political culture or organizational culture, or you name it. And these are important sometimes to be able to understand why we have different effects of the same treatment. That's how a simple or simplified version of a least squares model would look like. We basically have here fixed effects. So that's how you have it in the model, right? And you could have also, with fixed and autoregression, autocorrelation, you would also have lag-dependent variables. So basically, here you have unit at a particular time period t, and here you would have it at the previous time period to fix for the first order autocorrelation. And here we basically assume that, again, for treatment to be seen, to be realized in the outcome variable, some time will be needed. And t in this case could be year, week, day, 1 minute, etc. So it's just an example to show you how it would look like. So just about fixed effects, it's an extremely powerful tool, especially when you study complex entities like countries or regions or markets or companies again, right? And it is more appropriate for a small subset of units of analysis when you don't have any intention to generalize. And when, for instance, you study a universe of cases. You study all of the countries, so all of the companies that you're interested in. For instance, companies that declared that whatever they are increasing something or decreasing something, so you can study all of them, and you're not having any intentions to generalize from these results. You just want to understand the processes, underlining process and causal effects. But also in these settings, you are getting some limitations in a way. So for instance, given that you have this fixed effect that is basically a time invariant variable for each unit of observation, because your intrinsic characteristics do not change over time, right? It is a constant for you, but not for somebody else. So it is time invariant variables. So this cannot be included because, so the time invariant variables, other ones, cannot be included because this one variable will observe effects of all time invariant variables. But the same goes for slowly moving variables. If some indicators are progressing really slowly, you cannot include them because, again, it would lead to large standard errors and you would fail to identify effects when there were some effects, right? So basically type 2 error. And also when you have not that much data and you introduce for every unit of analysis, let's say country or company, you introduce a dummy variable, then by that you also reduce your degrees of freedom. So these models also come at a cost, even though fixed effects are a very powerful tool to fix for unit heterogeneity. And very, very fast, I know, I exceeded the time, but so understanding causality is intrinsically, essentially, is about understanding facts and counterfacts, understanding what the reality would have been had we not applied the treatment. In physical world, again, it is impossible. So we are trying to get as close as possible to these settings, and therefore statistical assumptions and tests therefore are essential. So you cannot do much without being sure that you control for everything. So this understanding of causality is very much based on Rubin model, Rubin causal model, as it is known in literature, and also John Stuart Mill, I think, yeah, John Stuart Mill, philosopher from 19th century, right? So they defined this logic of thinking about causality, about counterfactuals, and how life would have been had we not applied the treatment. So given that there are very strong assumptions, we have to be aware of that, and of course we need to have the domain knowledge, because you can't move far without having this domain knowledge. So you have to be very aware of what you do. And again, fixed effects are a very powerful tool for capturing unobserved unit-specific characteristics, basically for those variables that are time invariant, such as fundamental characteristics of individuals that could have possibly caused, for instance, smoking or some other type of behavior, as guys have mentioned earlier. Thank you for your attention.
So I'm going to be selfish because we don't have time for questions, but one thing that you mentioned was that the time invariant nature of these correlations actually induce more correlation. Am I right in this assumption? Please falsify me here.
Right. You have a point there. Right. So you have these time invariant characteristics that are intrinsically characteristic for different units of analysis. These are strongly correlated with other variables, other covariates in your model, of course.
So it means
you have it, yes. But when you build the model, so basically the essential idea is to explain something. So the things that are supposed to explain something else, they have to be correlated, right? Because these are phenomena that have to be, well, think for instance about explaining GDP. So you would include, for instance, like in this example, you would include democracy, you would also probably include export, and of course democracy and export will be correlated because that makes sense. I'm just making up this example, but just to say that, yes, this will be correlated because these are just dummy variables, right? So, and of course, the other features will be correlated with that, yeah.
Okay, cool. So we'll have a short break from this, but really, thank you, Karina.
Thank you.
Thank you so much.